So let's go back to identification. Identification is a set of assumptions of distributions. So if we think of all possible distributions over some set of covariates, exposure, and potential outcomes, what we did with our identification is restrict that. So we're not going to, we think that we're saying, I believe that in reality, we're in this restricted set where we have this additional condition. A is independent of y little a. And the reason that is helpful is because if we don't have identification, the observable estimates are estimands are uninformative. So here consider, this is the two causal data generating processes. And I'm telling you the true, let's say, causal ATE for this one is 0, and the true causal ATE for this one is -1/2. And now what happens if I map those distributions over into the observable distribution? So I hide my potential outcomes, and I say y equals to y of big A, and I ask, well, what's the naive ATE of each of these? I could have a case where for this one, the true ATE is 0, and here I can estimate it to be 0, or the causal ATE is 0, and here the observable ATE is 0. But for this one, which has a different causal ATE, I still get that the observable ATE is 0. So I kind of can't tell. Sorry, there should be a little 1 here. So my point is that I can't tell P1 star and P2 star apart based on just what I get to observe. These two look the same in terms of the anything that I can say about the ATE, and that's bad. Let me proceed here. So that difference is bad, and I can show you in a simulation. So here I'm going to have set up two causal data generating processes. In this first one, I have a binary covariate that takes 0, 1, and it has equal probability of being both, and then everyone here has equal probability of being exposed or not. And both y0 and y1 are 0, so basically the treatment does nothing. The same thing happens no matter what. In this setting, this other data generating process, I have the same covariate, but here the treatment is decided based on this really kind of interesting distribution where if x is true, if this person is a 1 here, so let's say this is like some genetic risk factor. So if they have this risk factor, then they are, I believe, less likely to be treated than if they don't. And then the potential outcomes look like this. So if they are at risk, then under no treatment, their outcome is 2. So that's bad. Higher is bad here. And then under treatment, their outcome is 1. According to their if they're not at risk. So it's a little complicated, but that's what this is doing. It kind of doesn't matter because my point is just that here I can define the true causal ATE by just taking the mean of y1 minus the mean of y0 by just drawing a whole bunch of data here, right? And the way that I've set this up, it actually turns out that the ATE for this causal data generating distribution is -1/2, and for this one it's 0. And now I'm going to make this like observable transformation function, which just takes one of these data generating processes, and then it just glues on these lines of code at the end. So we define y as being y1 if a is true, and y0 if a is false, and then we delete y0 and y1. So just think of it as gluing these lines of code on here as an extra mutate and select. And then we define P1 and P2 as the observable transformations of P1 star and P2 star. And then we can ask about the naive ATE. So here we can't use the ATE function on data drawn from these because there is no y1 and y0. So this code would just say, hey, where's y1? What are you talking about? So we have to define the naive ATE, which takes data drawn from one of these distributions, which is just y, a, and x. And I'm just taking the mean of y for the subset where a equals 1 minus the mean of y for the subset where a equals 0. And if I do that, for both of these, I get 0. Okay, and this is the discrepancy that I was talking about right here. So this is the problem that we have a case where we cannot tell these two distributions apart, basically. We get the same observable ATE, even though the causal ATEs are different. But the identifying assumptions basically rules out those cases. So under the identifying assumptions, my whole point with this whole thing is just that when we do these identifying assumptions, we're ruling out the cases where this bad thing happens. So we're just considering, like, let's say these are the set of distributions where A is independent from both of the potential outcomes, and this is the set of distributions that they map to under this observable transformation. And what we're saying is that for any distribution here, if this one, let's say this is P3, right? If the naive ATE of this is equal to 1, then whatever this 1 led to that, the true causal ATE is also equal to 1 over here. So you don't have this case where something is 0 and or something is 1/2 and then it maps to something that's 0. It just rules those all out. So we don't get these like weird collisions where we think something is going on when it's really not. So that is like the role of identifying assumptions and the way that you can kind of think about it graphically. Okay, so under the identifying causal assumptions, so here's a little bit of notation that basically summarizes everything that I just said into one little pithy equation, which is nice if you understand what it's saying, but otherwise can be a bit difficult to parse. So think of this as just a summary. So under the identifying causal assumptions, we can write that as a set. So M star is the set of causal distributions where such and such thing happens. So for example, where YA is independent from A. So for all P star in M star, this is the identified causal model, we have that the causal parameter, the causal estimand, is equal to the observable estimand evaluated at the observable transformation of the causal data generating process. So this little guy here, this is the P that we actually get to draw data from. And we're saying, okay, well, if we could draw infinite data from this and estimate this naive ATE, that would be the same as drawing infinite data from the causal data generating process and estimating the causal ATE, which is what I have here and here. So just a little pithy shorthand way of saying all of that, which is tidy. All right, so now that we understand that, we already saw this. This is this thing applied to the average treatment effect under randomization. The way that this would read is for all causal data generating processes where the potential outcomes are independent from treatment, in other words, treatment is randomized, we have that the causal average treatment effect is equal to the naive average treatment effect, which is great, but doesn't really do enough for us because we don't really have randomized data in most cases. And so what can we say in those settings?